The electrolyte in a lithium-ion battery serves as the medium for transferring lithium ions from the anode to the cathode during use or discharge of the battery, and vice versa upon charge. It is a critical component that influences overall capacity, electrochemical stability, and safety. An ideal electrolyte should exhibit high ionic conductivity, wide electrochemical stability, low volatility, and non-flammability. In this lesson, we will discuss composition and working mechanism of current electrolytes, the main issues related to the commercial electrolytes, the challenges for researchers in this field, and the most promising solution for next-generation batteries. Electrolytes in lithium-ion batteries are typically composed of a lithium salt dissolved in an organic solvent. The most commonly used lithium salt is lithium hexafluorophosphate, LiPF6, due to the good solubility in organic solvents, the wide voltage range, and the compatibility with many active materials, and the formation of a stable solid electrolyte interface. However, LiPF6 suffers from moisture sensitivity, leading to the detrimental formation of HF. For this reason, other salts based on bis-sulfonyl amide anions are also being explored for the enhanced chemical and thermal stability and the possibility of operating at higher voltages. The organic solvents typically used for the preparation of electrolyte solution are carbonates, such as ethylene carbonate, dimethyl carbonate, and propylene carbonate, or different mixtures of them. Such solvents are effective in dissolving the lithium salts. They also have a high dielectric constant, are stable within the typical voltage range, and present a good balance between ionic conductivity and viscosity, which is beneficial for the formation of a stable solid electrolyte interface. In commercial batteries based on liquid electrolytes, to physically separate the anode and cathode and avoid short circuits while allowing the transfer of lithium ions, a membrane separator is placed between the two electrodes, soaked with the liquid electrolyte. A high-quality separator must have excellent mechanical strength, enough porosity to allow the passage of the liquid electrolyte, thermal resistance, and electrochemical stability in the adopted voltage window. Modern separators are typically present a thickness of 10-25 micrometers and a porosity of 30-50% in order to balance ionic conductivity and mechanical integrity. Commercial separators are commonly made of polyolefin materials, mostly polyethylene and polypropylene, offering good chemical resistance and mechanical durability. Furthermore, those polymers perform also a shutdown function, preventing thermal runaway by melting over a critical threshold, thus blocking the ion transfer. On a lab scale, glass fiber filters are also used, being chemically inert and resistant to high temperatures without shrinking, allowing for an excellent electrolyte absorption and retention, and easily adapting to different shapes and configuration. Despite the extensive use in commercial devices, liquid electrolytes based on organic solvents entail some concerns about their long-term viability. Indeed, the inherent flammability of the organic solvents poses significant safety risks, since they can easily ignite upon short circuits, leading to potential thermal runaway and catastrophic failure. Furthermore, their volatility is compounded by the risk of leakage, which not only compromises the battery performance, but also causes environmental and health hazards. Beyond safety concerns, liquid electrolytes suffer from limited electrochemical stability. Over many cycles of charge and discharge, the liquid electrolytes inside the battery degrade, forming unwanted byproducts that diminish battery efficiency and lifespan. In industrial practice, these problems are mitigated by the use of additives in electrolyte composition, no more than 5 weight% of the whole solution, to improve the electrochemical stability, optimize the formation of solid electrolyte interface, reduce the consumption of active material in irreversible reaction by acting as sacrificial agents, lower the viscosity to increase the ion mobility, and reduce the risk of thermal runaway by introducing flame retardant features. Academic and industrial researchers are actively seeking alternatives to liquid electrolytes based on organic solvents, aiming to solve their main issues and develop more reliable batteries. The most straightforward solution is represented by the use of different classes of solvents for the electrolyte salts, such as room temperature ionic liquids and deep eutectic solvents. In particular, ionic liquids offer higher safety and stability, thanks to the very low volatility, non-flammability, and low toxicity. They can operate at high temperatures without decomposition, even above 200 degrees, withstand high voltages up to 5 volt versus lithium, and are chemically stable upon prolonged cycles of charge and discharge, improving battery lifespan. However, ionic liquids suffer from some drawbacks, such as the high viscosity that reduces ionic conductivity and causes higher internal resistances within the battery, and their difficult and expensive preparation that makes their use still economically unfeasible for large-scale commodities. On the other hand, deep eutectic solvents are cheaper and easier to prepare than ionic liquids, since they are made from naturally abundant and biodegradable materials mixed together without requiring complex purification steps. They also offer great advantages in terms of non-flammability, high thermal stability up to 200 degrees without decomposition, and environmental friendliness in case of leakage. However, they are typically more viscous than conventional electrolytes, thus affecting the ion mobility, and they can easily react with some common electrode material, so further research is needed to enhance their compatibility. A breakthrough can be represented by the development of solid-state electrolytes. Initially proposed by academic research, their application in commercial batteries is now being explored by some companies. Solid-state electrolytes offer several advantages over liquid ones. They are generally safer, more stable, and more easily recyclable. However, they still present some limitations, such as low ionic conductivity at room temperature, poor interfacial contact within the electrodes, and mechanical brittleness. There are three main classes of solid-state electrolytes: polymer, ceramic, and composite. Polymer electrolytes, including both totally solid electrolytes and gel-like electrolytes, where a fraction of liquid solvents or plasticizers are trapped inside, are made from polymer matrices, such as polyethylene oxide, PO, or polyvinylidene fluoride, PVDF, which incorporate lithium salts for ion conduction. They offer better safety than liquid electrolytes, improved flexibility, and good processability. However, their ionic conductivity is generally lower, especially at room temperature. Ceramic electrolytes are constituted by fully solid and inorganic materials, such as garnet-type oxides, like lithium lanthanum zirconium oxide, superionic conductor phosphates, typically called nasicon, or sulfides, although their use is limited by the risk of forming very dangerous hydrogen sulfide gas upon reaction with moisture traces. Ceramic electrolytes offer high ionic conductivity, excellent electrochemical stability, and strong resistance to lithium dendrite formation, making them ideal for next-generation solid-state batteries. However, their brittleness and processing challenges limit widespread adoption. Finally, composite electrolytes combine polymers with ceramic or inorganic fillers to enhance ionic conductivity, mechanical strength and stability, while maintaining flexibility and ease of processing. In conclusion, the evolution of electrolyte materials is pivotal for advancing the performance, safety, and sustainability of rechargeable batteries. While conventional liquid electrolytes have enabled widespread commercialization, their inherent safety risks and stability issues necessitate the search for better alternatives. Innovation, such as the use of other classes of solvents or the development of solid-state electrolytes, offer promising improvements, but are still hindered by practical challenges related to production cost, difficult processability, and limited working conditions. Further research is crucial to address those current limitations, thus allowing for the realization of next generation of safer, longer-lasting and higher-performing batteries.